All right, morning everyone.
Good morning.
Hope you enjoyed the ice. Okay, woohoo, I know, right. So, that means we're gonna be a little bit behind where I was planning to be in terms of what we're talking about in class. But it actually kind of works out because, these 2 weeks we're kind of doing like these, this 2 parts of the VM translator, so it's kind of all related. And obviously, if you felt unprepared to, complete the project that was due yesterday, you could take an extension, and many of you did, so that's totally fine. So I do want to finish up, oh wait, before I do that. So we'll kind of finish up what we were planning to talk about last time, which will be for, project 7, and then probably today we'll start in on talking about stuff for project 8. But it's all part of the VM translator, so it'll all be related. So let me just, there was something I was going to show you on the website, and now I can't remember what it was. Oh, yeah, I wanted to look at the notes I wrote last time, just to kind of remind ourselves, just to like load this back into everyone's brain, because I know, even for me, I said it all, and I'm like, okay, wait, what did we talk about last time? So, okay, we talked about what a virtual machine is, blah, blah, blah. And remember, so this virtual machine, the hack virtual machine, it's a stack machine, so everything kind of deals with this stack. And there's basically 4 kinds of instructions that you're going to have to figure out how to translate into assembly. Right? There's memory access commands, and we talked a lot about those last week. Right? That's the push and pop commands, where you push and pop from or to these different segments, and they go onto the stack or get popped from the stack. We'll probably talk a little bit more about that today. And then some arithmetic and logic commands. We'll talk about this today. These are not really that hard, though. Definitely compared to these are not that bad. And so this is project 7, these 2. Right? So project 7 is just, can you get these commands to work? And the tests only use those commands. They don't use the other commands. And so if your translator can translate those, then you'll pass those tests. But it's not a fully working VM translator yet. For that we need also, so branching is like, jumping, right? And that is also not too bad. The really interesting and more difficult part of project 8 is getting function calls to work. So this is the big difference between the virtual machine language and assembly language. The assembly language, all it has is jumps, right? But the virtual machine provides the ability to call functions, and it kind of, you can call a function, and then when it's done, it can return, and it can come back to you. So when you're writing VM code, you can actually think in terms of, I'm defining a bunch of functions, this function calls this function, which calls this function, and it'll, that works just like you would expect it to work from writing, any programming language that you're familiar with. But obviously a lot has to go on under the hood to make that work, so we'll talk about that. We may or may not get to that today, but we'll definitely talk about it. If we don't get to it today, we'll definitely talk about it a bunch on Thursday. Okay? So that's kind of where we're headed. And then, And then we talked a bunch about, honestly, it's like a lot of stuff to throw at you, right? And you feel free to use this as like a reference, right? I don't expect you to remember all this stuff that we talked about. But we might, let's see, let me think if I want to talk to some about this. I guess I want to say, right. So again, just to remind us, right? So we talked a bunch about, we have push and pop. Push puts something from some memory segment onto the stack, and then pop pops something off the stack and puts it in some memory segment. And then, and so that involves like, you know, incrementing or decrementing the stack pointer appropriately, copying stuff around in memory. And there's these 8 segments. And I think I did them in an order that's not helpful because some of them kind of go together. So let's think about this. Argument, and maybe I should just, okay, you know what? Okay, I'm gonna come back to that because I'm gonna write this. I'm just looking at a PDF right now. So, just as an example, right? We looked at an example of, I think, you know, pushing onto local or something like that. Yeah. So we did this example of push local 3. So definitely feel free to come look at this to help understand like what kind of assembly code you have to generate to do that. And remember that each VM instruction will probably turn into a whole bunch of assembly instructions. Okay, so that was what we did last time. And then, yeah, I want to briefly say, so we've got these 8 segments, so it's like argument, right? So argument holds the arguments of the current function. Local holds the local variables of the current function. And then we also have this and that. We haven't really talked about what, I think I mentioned we're going to use these. This is going to be used for objects, like if we have some current object. And that is going to be used for arrays. So if we have like a current array, that will point to the current array. The point is, all of these, where they actually are in memory will change. So it's like, well, right now we're in this function, so argument points to this area of memory where that function's arguments are stored. But if I then call another function, argument is going to change because now we have to point to the place in memory where that function's arguments are stored. So all of these, right, there's a register that stores the address where those segments are located. Right, so these all can change location. Their location is stored in a register. Okay, so this is like indirect addressing, right? Where in order to say, you know, push to the local segment, and this was in the example that we did the other day, I have to first get the value of that register, which is the address of where the local segment is, right? Then I take that address and I maybe do some math to it if I need like an offset. I say, oh, that address +4 or something. And then I look up there. So I'm doing 2 memory lookups. One first to find out where that thing is, and then another one to actually go, you know, get that thing. But these are all very similar. So in particular, right, you should be able to have like one function, for example, that generates similar assembly for all of these, right? And there's just small differences, like in terms of what register you look up. You know, is it the argument register or is it the local register or whatever? Okay. Then we have pointer and temp. Let's see, 1, 2, 3, 4, 5, 6, and there's constant. What's the other one? There's one I'm forgetting. Anyone know what it is? Static, yes, thank you. Okay. So static and constant. So these ones are similar. But these ones, like, the pointer segment is always in the same place. It's always at like, I think it's 3, right? And temp is always at 5, right? Pointer is a little funny. Basically, the pointer segment is where the this and that registers are stored. So if you want to change the value of this, or if you want to change where this segment is stored, you can just say, like, push something to pointer 0. Which says, okay, pointer 0 is the 0th place in the pointer segment. The pointer segment just has the this and that registers. And so that would change the value of this, which means now, conceptually, if we do something under this segment, it's going to be somewhere different. But the point is, so these are always in the same place. So this is direct addressing. Right, so the code for these is simpler. The code that you have to generate for these is going to be simpler because you don't have to do this double memory lookup. Right, you just know, like, if I want to do, pointer 0 or pointer 1, it's like I just either look at memory address 3 or memory address 4, and then I just do something right there. Same for temp, right? If I want to do temp 5, I just do 5 plus 5, that's 10, so then I look at 10. Okay. And then static is kind of funny. Basically, if I want to say, like, if I want to do, like, push static, J, where J is like some variable name, we just turn this into, like, at, file name dot J. So we're basically, so you don't actually have to do very much work when you're generating the assembly for this, because we're basically like relying on what the assembler already gives us. So if I say, oh, where am I storing the static variable J? Well, I'm just going to give it a name, and then I'm going to let the assembler figure out where to store it. It'll just like make up a, just like, you remember how your assembler said, oh, this is a variable, I haven't seen this, so I'm going to give it an address starting at 16. That's what we're going to use for the static variable. And then constant, right, this is just like, remember the constant segment doesn't actually exist. It just means if you say like pop constant 3, or like push constant 3, it just means push the number 3 on the stack. So that's also pretty simple because it's literally just take that number, put it on the stack, which is like, maybe 4 assembly instructions or something, right? Because you've got to, well, here, let's if I did like, push constant 7, right? How would I translate that to assembly? Just as a warm-up.
At 7.
Okay, so I can do at 7. That'll get the value 7 into the A register, right? D equals A. Okay, so I can copy it into the D register. Probably helpful. Just save it. Because now, what do I need to do? Now I need to, like, I've got my stack here. I've got my stack pointer, right? So I've got, like, maybe here's my stack. I've got some stuff on the stack. My stack pointer points to, the next available memory location on top of the stack. So now what do I want to do?
Add it to the stack?
Add it to the stack, yeah, how do I do that? Oh, I just use the assembly instruction, push onto the stack, right? If only. Okay, well, first of all, I need to copy that 7 value, I need to copy it right here. Right, so how do I do that? How do I get that value to be stored there in memory? What was that?
Is it M equal to D?
M equal to D? Yes. But what address is it going to use to do that? I need to tell it what address to use. So what should I put? I need to put something here.
SP.
At SP? Yeah. Okay. Am I done? No, because I also need, so now put the 7 here. What else do I need to do?
Increment SP.
Right, I need to increment SP. Simon, are you gonna?
I think instead of SP, you have to include A equals M, because it's an indirect address.
Ah, very good. Yeah. So this actually is not quite right. So, think about what this does. So, somewhere in memory I've got like, here's my, here's actually the stack pointer. It's actually stored at like memory address 0 or something like that. I don't know. It's stored somewhere. So if I just say at SP, it's like, okay, 0 is now in the A register. And if I say M equals D, it's now putting 7 there. That's not the right thing, right? Because now that means, oh, the stack is suddenly like, pointing somewhere like address 7, which makes no sense. All right, this is going to wreak havoc. Now your stack is overwriting all the like special registers and stuff, right? So this is not a good idea. So, right, I don't want to do that. So what were you saying, Simon? What I need to do?
A equals M.
Right. So I say, okay, read from where the stack pointer register, it has some address in it. Read that address and put it in A. So, let's say maybe this is like, address, this is like 506, 507, 508, right? And the stack pointer actually stores the number 508, right? So right now, when I say at SP, A register has 0, wherever the stack pointer is. Then I say A equals M. It says, okay, go read the memory here, go read this location memory, and store that number, 508, in the A register again. So now the A register is pointing to this location in memory. Now I can say M equals D. Okay, so if you, like, this is one of the really key ideas that often trips people up. It tripped me up when I was doing the project, right? This idea of like, kind of needing to think really carefully about, memory addresses that hold other memory addresses, and you have to think really carefully about like, okay, is this the value that I want, or is this the address of the thing that I want? So like I need to do another lookup to get another address to then go look up something else. Right, so even just pushing the constant 7, we do have to do this kind of double lookup thing because the stack pointer has an address and we need to go look there. Okay. So now I need to increment the stack pointer, right? Because I need to know that I've pushed something on and now the stack is 1 bigger. So how do I do that?
Is it at SP M equals M plus 1?
Yeah, that'll do it. And here I don't want a separate, I really just want to look, here at the stack pointer and just like increment the value that's actually stored right there. So this would now store 509, which means, conceptually, it's like the stack pointer is now kind of pointing to this thing, the next thing up. Okay. Cool, so you can look at this as an example. You can also look at the example we did of like doing the push local 3. We did that example in class last time, so you can look at that. Hopefully these will help you. Right, and even when I said like push static J, like this is where that static variable is stored, but you have to read from there and push on the stack. So you're going to actually be doing something kind of similar to this in terms of getting that value and then pushing it on the stack, doing something very similar. In fact, you might even consider, having like a single function that will generate some assembly code to push a value on the stack. So for example, I think when I did my project, I said, I had some code that said if I know that the value I want to push is already in the D register, then I can generate some code that'll push it on the stack. And I think in some cases it's maybe like not quite as efficient as it could be. You could save a few instructions if you did it more directly, but it saved me time to like make some functions. So, so you're welcome to consider things like that. Okay, so any questions about that before we move on? Okay. So let's talk about doing arithmetic on stacks. I'll go back and find in my notes where this is. And I want to do a couple examples first, just to show kind of how versatile this idea of using a stack to evaluate things is. So example, if I have like x plus y times z. So of course you all know like order of operations, blah, 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 right? Like the y and the z are gonna get multiplied, and then we have to add that to x, right? I can't just go left to right and just do things as I see them. So this is one of the big differences, right? All the languages that we've been talking about so far, and all the translations we've been doing, you know, we're just going through, you know, each thing translates directly into something else. Like as we're reading it, we're just doing it directly, okay? I mean, this is at the level of like what the compiler is going to do, and in fact, actually, the compiler that you're going to write, it's going to insist, the language that we're going to use, it's going to insist that we have parentheses everywhere. So you don't even have to worry about this in the compiler. But I'm just telling you, like, this is the kind of thing that real compilers have to worry about. It can't just go through and translate it thing by thing as it sees it, because it's like it actually has to do the multiplication first, and then do the addition, right? But the way this can work, right, is that we first say, we're going to push x on the stack, and then we're going to push, we're going to push y on the stack. So we can kind of go through as we're seeing things, like the variables x, y, and z. We can just push them on the stack. Now I don't want to do anything with x and y yet. Right, this is the nice thing about the stack. The stack remembers that we have x and we have to do something with it later. So I'm going to push z. Okay, and now I do the multiplication. So what I'm going to do is, how does a multiplication work on a stack? Well, you pop the top two things from the stack, you multiply them, and then you put the answer back on the stack. Okay, so I'm running out of space here, but let's see. Multiply, right? This is like pop top two, and multiply, and push. And then, of course, we do the addition, which is going to pop the top two things, add them, and push the result back on the stack. So x plus 1. And so in the end, right, I end up with just, you know, the thing that I computed sitting on the top of the stack. And I'm not going to like prove it to you, but yeah, basically we can always evaluate any kind of expressions in this nice way using a stack, where the stack is keeping track of the stuff that we have left to do still. And we always just do an operation on the top two things, push the result, and then we can keep going. Garrett?
So is there some need for these to be in like the right order of like PEMDAS, or would we have to come up with that ourselves to sort them as we're adding them?
You are not going to have to do this. Real compilers have to do this. Like, how does it know when to do the multiplication and when to do the addition? It knows how to do that because it is taking into account the order of operations, right? But as I said, that's kind of beyond the scope of this class. It doesn't really teach you anything about how computers work. It's just about how kind of compilers give us fancy, nice notation. But if you want to learn how that works, you can take my programming languages class next year. But anyway, the point is just that a stack is a really nice way to organize you know, how this can work. So like if we did, on the other hand, if we did like x times y plus z, we can still push things in the same order. The difference is just when do we do the operations, right? So we say like, okay, first we're going to push x, then we push y, then we go ahead and do the multiplication right away because we're supposed to multiply them, right? So then I pop them both from the stack, I multiply them, and I push the result back on the stack. And then, oh, I'm making like stack snakes or something. Then I'm gonna push z, and you know, x times y, I push z, and then finally I'm gonna add, I get x times y, z. You know, and you can even imagine, I'm not gonna write, if we had like, you know, x plus 3 times f of, you know, 9 minus y, comma, g of, x. Right, so here's like this complicated expression that involves doing some arithmetic, doing some function calls, right? Function calls inside function calls. And I claim I'm not going to draw out the same kind of picture, but maybe I'll talk through it. I'm just trying to intuitively convince you that a stack is the right way to organize this to keep track of what we're doing. Because of course, like you can write this as one line of code in a high level language, but you know, at the level of assembly language, this is going to turn into a ton of instructions. And how do we keep track of what we're doing and what we have left to do, right? So the way this would work is, well, we first push x on the stack, then we push 3 on the stack. We're not ready to do anything with them yet, right? Because the 3 we still have to multiply by something first. And then, well, I need to call the function f, but first I need to figure out what its arguments are. So I'm going to go ahead and push 9 on the stack. And then I'm going to push y on the stack. And now I can go ahead and do a subtraction. So I do a subtraction, I pop those two things, subtract, put the result back on the stack. I now have x, 3, and 9 minus y on the stack. Right? Then I push x on the stack, and I call the function g. Right? And g basically just sees that it's, you know, it's looking at the top of the stack, and that's its input. So g might do whatever it does, maybe by pushing more things on the stack, but ultimately, when it's done, it'll leave its result on the top of the stack. Right? So now we've got x, 3, 9 minus y, and whatever the result of g is on our stack. Because g didn't touch the stuff we already pushed, right? Because that's the stuff that's waiting. And then finally we call f, right? And now f has its 2 inputs on top of the stack. It does a whole bunch of stuff and leaves its output there. And then we do multiplication. Now we get the waiting 3 and the output of f get multiplied, and then we do an addition, and finally it adds its x, right? So the stack is helping organize kind of all of the stuff that's kind of in process. And even, as we'll see, even like the fact that I'm calling these functions, the functions themselves will store some stuff on the stack to say like, okay, you know, what are my arguments, what are my local variables, where should I jump back to when I'm done, all that kind of stuff, okay? So the stack is kind of our central data structure for everything. Okay. Oh, as an interesting aside, you know, like if stack languages are so nice, how come, you know, we don't just program using stacks all the time? So there is a language called Forth, which is an attempt at making a high-level language that's based around like stack evaluation. So everything in Forth, there's like a stack, and everything that you do operates on the stack. It turns out, even though it's like it's really nice conceptually, just humans don't think that way, and it's kind of, yeah, it's just kind of weird and awkward to use. So, or maybe it's just that we're so used to languages that, you know, we're so used to this kind of notation that that doing it with everything with the stack is kind of awkward. But anyway, I don't know. All right, so let's talk about what arithmetic instructions that you have to implement, or what the virtual machine language gives us that you have to translate to assembly. And this is the last bit of project 7. If I can find the right page here. Here we go. So new page. So we have add, sub. Right, so these, the add instruction says, take the top 2 things on the stack, add them, and push the result back on the stack. Right. Sub is the same thing but subtraction. Right, there's neg, which is unary negation. Not like logical negation, I mean arithmetic negation. And then it has some EQ, GT, LT, and or not. That's it.
Oh, no molt?
No molt, no. So yeah, I mean, we already know that our actual CPU doesn't give us multiplication. And the question is like, where are we going to add it? At what level of abstraction are we going to introduce multiplication? It's not here. So the virtual machine doesn't support multiplication either. We're going to do it yet another level up, right? When we get to the high level language called Jack, that's going to translate to the virtual machine language. It's going to have some code. We're going to be able to write some code in Jack that will do multiplication. So we'll be able to use multiplication in our programs, but it basically gets turned into some Jack code. That gets compiled down to a whole bunch of additions and stuff, right? But it's going to be more efficient than the multiplication that you all did like on project 4 or whatever. Or you had to do like this mult ASM that just like added the thing repeatedly. It'll be more efficient than that, but it's still going to use addition. So how are these going to work? So conceptually, for example, like the neg command, conceptually it pops the thing off the top of the stack, negates it, and then pushes that answer back on the stack. Okay? But you don't actually have to implement it that way. In fact, you shouldn't. Because it would be a little silly to like, you copy it out, you like decrement the stack pointer, and then you like do the negation, then you put it back in memory, and then you increment the stack pointer again. The stack pointer ultimately is going to end up in the same place where it was. Right? And we can just like negate it in place, just like on the stack. So you can say, get the address of that thing on top of the stack, and just negate it. Right? So like this one you can like just negate top of stack in place. Right? So you'll have some kind of instruction that's like m equals negative m. Of course, you have to figure out how to get the right address. Of course, and it's not just SP, right? It's like one less than SP, because SP is always the next spot above the top of the stack. How about add and sub? So these ones are binary. So if I have like x and y, right, I want to, and here's my stack pointer, I want to end up with something that looks like x plus y, and the stack pointer is here. So again, conceptually it says pop the top 2 things, add them, and push the result back on the stack. But we're not going to implement it quite that way, right? We really just need to decrement the stack pointer 1, and we could like get the value here, get the y value, decrement the stack pointer, and then add the y value directly to this place in memory. It's just like by hook or by crook. If it starts looking like this, you need to get it so it looks like this. It doesn't really matter exactly what happens in between. As long as conceptually it is as if you popped 2 things, added them, and pushed the result back. Does that make sense? Now, for addition, it doesn't really matter which one is x and which one is y. For subtraction, it matters. You have to get the order right. And it's tricky to think about it. So, but the way I like to think about it is, well, if I do subtraction, let me just put this here. Get the order right. Remember, if I have like x minus y in some high level language, it's going to get translated into push x, push y, subtract. So this means push x, then push y, then subtract. Okay, so it's going to look like, it will in fact look like this, where the thing on top of the stack is actually y, is the second argument. So, but you know, it's confusing because that's the first thing that you pop. The first thing that you pop is actually the thing you're subtracting from the other thing. But if you just remember this, right, and remember it's going to look like this, you'll get it the right way around. And you know, if you get it the wrong way around, you'll figure it out, and then you just switch them, and then you get it. So these ones are very similar. I mean, it's really the same thing, right? It's just like, no, not. Not is unary. Not is very similar to negation, right? And so you probably even could like have the same function that handles like, you know, add, sub, and or. Because the code that you generate is going to be very similar. The difference is just like what operation are you doing on the two things? Are you anding them, or are you? And the ALU supports all of those operations just in one instruction, right? So that's fine. These ones are a little more interesting. So what do these mean? Let me. I haven't actually told you what the semantics of these things is. So for example, EQ means pop the top two things from the stack, compare them, and if they're equal, push -1, else push 0. Why do you think we would use -1 if they're equal? Yeah, because it's all ones, right? It's just like true, 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 versus false, 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 false. I mean, so I say -1, but really it just means like push the value that's all ones. And this is push the value that's all zeros. It doesn't really matter, honestly, what we use, as long as we're consistent in interpreting it. But this seems a simple choice. So this, like, the ALU doesn't do this directly, right? There's no way to, like, if I get these two values, there's not a single ALU instruction I can do to say, see whether these two things are equal, and then, like, you know, push this in the stack. I mean, obviously I'm going to have to translate this into a bunch of instructions. Garrett, you have it?
I was going to say, couldn't you just use and to check?
Just use and to check if they're equal? I don't know, could we? Yeah, what do you think?
I was thinking XOR.
Or XOR? What do y'all think? Could I use, let's start with and. Could I use, so I think Garrett is suggesting, can we use the ALU's and instruction to implement the equality test? If I have two values and I want to check if they're equal, can I and them? Will that give me something useful? Matthew, why not? You're shaking your head.
Because the value is like, I don't know, like 0, 1, the output would be, I guess in that case it'd be 0 and 0, but if they were
Right.
different, like 0, 1, 1, and 1, 1, 1. Or 1, 1, 1, and maybe it does work out. 1, 1, 1, and 0, 1, 1. The output would be 0, 1, 1. It would
Right.
be like true or false.
Yeah, I mean, so building on that example, like if I had 0, 1, 1, and 0, 1, 1, and I AND them, I get 0, 1, 1. But also if I have 1, 1, 1, and 0, 1, 1, and I AND them, I also get 0, 1, 1. So I get the same answer whether they're equal or not in that case, so, yeah. Collier, you
I think we can use AND if we subtract one from the other first, and then AND it to 0.
Okay, yeah, so if we subtract one from the other first, in that case, like, we just wanna know, did we get 0 or not? And actually, in that case, the ALU gives us that, can tell us whether it was 0 or not, and we can have a jump based on whether it was 0 or not. So we don't even have to use AND at that point, we just say, jump if it was equal to 0. That's probably the simplest way to do it. But was there, Garrett, you ever?
That's what I was going to
You were
say.
gonna say, okay, yeah. Daniel said something about XOR, so I think XOR actually works also, because when you XOR things together, right, if the two bits are equal, you get 0, and if they're not equal, you get 1. So basically, if I XOR two values, the only way I'm gonna get all zeros is if they were exactly the same. They're gonna like cancel each other out. In any other case, I'm gonna get something that's not all zeros. So that's actually a nice idea. You could, instead of subtracting, you could XOR them, and then see if the result is 0 or not. However, that's not gonna work for greater than and less than. For greater than and less than, you really do have to use subtraction. So yeah, so this is the idea, right? We're gonna, so how are we gonna do this? We're going to subtract the two values on the stack. And then all I can do, right, is I can jump based on whether the result was, 0 or greater than 0 or less than 0 or whatever, right? So if 0 jump to, we'll just make up a label here, 0. And then, so if I do jump here, what do I want to do? So if the result was 0, that means these two things were equal. So I should push -1, right? Which of course is actually like, 5 or 6 assembly instructions. We've talked about that. What do I want to do here? So if I didn't jump, right, what should go here?
Push 0.
Push 0, yeah, because if I did not jump, that means they were not equal. And so I should push 0. And what?
Jump past the thing.
Right, I have to put another jump in here, because I don't want to keep going and do this part also. Right? So I could put another, put another label here that says, end. And this is like, jump. Jump to end. Something like this. And of course, this is like pseudo assembly, right? Each one of these things is going to expand into multiple lines of assembly to actually do this. Okay?
Does it go through 0 regardless, or would it only go through 0 if you jump to 0?
Well, that's why we put in this jump to end here. So if we go here, we're going to push 0, and then it says jump to end, so we're going to jump down here.
Okay.
Because we don't want it to do, I mean, if we didn't have that here, then it would be a problem, right? Then it would always
It
go
would
to
just
0.
go through 0.
Yeah, for sure. Yeah, so like really this, when I say jump to end, it really means you say like at end, jump. When I say push 0, right, well, we have to do a whole bunch of instructions to like get the stack pointer, put the, get the address, put the 0 there, increment it, all that stuff. one potential problem here, right? So this is like how we would translate an EQ instruction. So I'm reading a virtual machine, some virtual machine code, and I'm translating it to assembly, right? What if there's multiple EQ instructions in the program, and I'm translating them like this? What would the problem be, or the potential problem? Sammy, what do you think?
All your jump points are named the same.
Exactly. Like, if I always name this 0 and n or whatever, every single EQ instruction I generate is going to have the same labels, right? That's no good, because basically the first one depends how you implemented the assembler, right? Maybe the first one that it comes to, it'll save that in the symbol table, and then it'll ignore the rest. Or maybe like it'll always put it every time, and so it's like the last one that'll end up in the symbol table. In any case, like most of them are going to end up jumping to the wrong place, because like this EQ instruction is going to jump to that one down there. Any ideas? How do you think we might get around that problem?
Label them by which one it is, so like 0, 1, or 0, 2.
Okay, yeah, so maybe just like keep a counter of how many of these we've generated and just like stick the counter on the end?
Mhm.
Yes, perfect. We just need to do something so that they're different. And honestly, you don't even really need to count like EQ instructions. Just keep a global counter. Every time you need to generate a label, just like stick the value of the counter on the end of whatever name you want, and then just increment the counter. That guarantees that all your labels are different, right? So we actually want to do something like, 029, and this is like, N30, something, whatever. You just need a way to generate unique label names. Right, so for example, you can keep a counter and increment each time. Honestly, you could just name the labels. Well, no, you can't do that. You can't just have the label being a number, because then it would not interpret it as a label. You could call all your labels L followed by, the number of the counter. That would be a little hard to read, so it might be nice to give them some kind of names with numbers so that when you're looking at the output of your translator, you can kind of read it. But ultimately, it doesn't matter, as long as they are unique. Right, so in practice, your program is going to get here, it's like, okay, I need to generate some stuff. So first, I'm going to create some labels. So I'm going to call a function that I have to give me, I'll tell it, hey, I want a label that's called 0. And it's like, oh, here you go. It's actually, it should use 029. And you're like, okay, cool. So now you can just use everywhere you need, this should say 029 also. Everywhere you want to use that label, you can just use whatever that function gave you back. And you're like, oh, here, I need another label. I want it to be called something like n. And it's like, oh, here, use n30, because that's the next free number that I have. All right. Greater than and less than are very similar, right? Except instead of jumping if it's 0, you're jumping using some other condition. You have to be careful here that you get the order right also, right? But I'll let you think about that. Just think about what order things get pushed on the stack. Okay. Questions? Other questions? Or are you asking questions? Simon?
So to do greater than or equals, would we have to do that in multiple steps?
Yeah, good question. Right, so apparently the virtual machine does not give us the ability to test if something is greater than or equal to. So how would you do that? Anyone?
If it's greater than, or if it's equal to.
Yeah, so one thing you could do is you could translate it into compute greater than, and then also compute equal, and then do the or of those two things. There's a simpler way, so that would work. There's an even simpler way we could do it. Garrett?
If you do greater than first, then you know it's greater than, and just only if it's false do you go on equal.
Okay, so you could translate it into kind of like a nested if, where you say try greater
Less
than, and then if it's not greater than, or if it is greater than, then I'm gonna, or wait, yeah, if it's not, then I'm gonna check if it's equal. You can do that, there's an even simpler way. Jonathan?
Subtract one and then do greater than?
Subtract one and then do greater than, what do you mean? Oh, ha, I had not thought of that. That doesn't work. I like it, it's really clever, it doesn't quite work. Does anyone know why? So does everyone understand Jonathan's idea? So if I wanna see if like x is greater than or equal to y, I could first subtract one from y, and then just check if it's greater than. If they were equal, now y is one less, and so it'll actually be greater. And if it was greater before, well, subtracting from y doesn't change that, right? And if y was actually bigger, then now they're equal, but they won't be greater than. So that sounds really good, but it doesn't quite work. Does anyone know why that doesn't work?
Is it the exception of 0?
I don't think 0 is the exception. There is an exception though. Simon?
If y is 1 greater than x.
If y is 1 greater than x, it still works. Because if I subtract 1 from y, now they're equal, and if I check greater than, it will say false, which is the right answer. Garrett?
Is it something to do with negative numbers?
Yes. Matthew?
Because when you get to all negatives, then it would go back to the...
Yeah, exactly. The problem is like if y happens to be the like most negativist negative number and you subtract 1, you get like a really big number, and now that breaks. So it would work if we didn't have this like finite number of bits that we're storing numbers in. Okay, so I'm gonna think of another way to do it.
Not
To implement
less
greater
than?
than, what was that?
Not less than?
Not less than. Yeah, that's the way to do it. You check if they're less than, and then you just do not. And that gives you greater than or equal to. That's the simplest way to do it.
Thanks, probability.
Yeah, Simon.
Technically, the simplest way to do it is in assembly, because it works in assembly.
You're right. Yeah, it's like assembly can test greater than or equal to, so but our virtual machine doesn't have it. So I mean, this is an interesting point, right? Like the machine actually provides facilities that we're kind of not making use of. And there's a trade-off, right? I mean, you could make the virtual machine language more complicated in order to save a few instructions, you know, or you could choose to make it simpler at the cost of, you know, doing certain things is going to require kind of more assembly instructions than in theory you could get away with. One of the ways that you know, real languages deal with this is that I mean, there's a few ways, right? One is maybe you notice certain patterns and you're like, wait a minute, I noticed that this program is doing a less than and then immediately negating it. And I can just notice that, oh, I have a special case to generate some assembly code for that just uses the greater than or equal to test instead of literally translating what it says. You know, or yeah, maybe you just add something, another feature to your virtual machine language. But I hadn't thought of that before. That is an interesting point. I don't know exactly why they made this choice, but yeah. Okay. All right, so that's it for project 7. And some of you already know this, but I just want to emphasize it again. Don't feel like you have to finish the project before you can turn it in and get any kind of feedback from me. right? If you're working on it, I mean, so of course, certainly if you have a bug and you're like frustrated and you can't figure out what's wrong, please come and ask for help, and I'm happy to help debug. But honestly, if you're just like, I don't have any like specific issues right now, I would just like some feedback, because I'm just like not feeling confident whether I'm doing this in the right way, or like whether it seems like maybe I'm doing this, it's too complicated, there's a simple way, right? Send it to me, say, hey, would you mind taking a look at this, giving me some feedback? I'm very happy to do that and like kind of work with you through the project, instead of just like at the end, I'm like, yes, you get credit, or no, you don't. I mean, obviously if you don't, I'm gonna give you some feedback, but I just felt like I should say that now, especially as the projects are getting a little bit more involved, that there's more stuff that you have to do kind of along the way, and I'm happy to help with that as you go. All right. So for the last few minutes of class, I want to start talking about what we're going to do for project 8, and so that's right. There's two kinds of instructions that we haven't talked about yet, which is like branching instructions. That's going to correspond to like doing jumps. I mean, obviously, some of the stuff that we're doing, some of these instructions, already we have to do jumps in assembly to make it happen. But specifically, if we want to have virtual machine programs that have like if statements or while loops or stuff like that, and then function calls.
Oh, we're gonna do loops.
What was that?
I said, oh, we're gonna do loops.
Right. Loops, yeah. Oh, okay. My pen is dirty. All right. So while my pen is like charging for a second, so let's talk about the branching first, because actually the branching is not bad. It's really like the function calls that's going to be the majority of project 8. So the virtual machine language has 3 instructions that have to do with branching. So there's a label instruction that just literally means, you know, we're labeling this place in the program with a certain name. And that literally you're just going to translate it into a like parentheses label thing in assembly. So that's super easy. There is a go-to instruction. You just say go to label, and it just means jump to that label, and you translate that to a jump. I mean, you just like say at label, and then you just jump. Easy. And then there is an if go to instruction. Let me see if my pen works now. Somehow, like it refuses to work, and if I just charge it for like 10 seconds, then it's okay. Just like what? Yep, there we go. All right. So branching. So label, you know, name. It just gets translated into, you know, a label in assembly. This is another reason that you want to like, you know, the labels that you're generating like up here. How does this work? I forget. Maybe I should probably think about this and say something about it next time. Because of course, like you want to make sure that someone doesn't accidentally, like if someone uses a label, a name for a label that you happened to generate in one of your like automatic generation schemes, that would be bad, right? Because now suddenly stuff is jumping where it shouldn't. I don't remember how I dealt with that when I did the project, and I don't remember off the top of my head if the book talks about that. I'll talk about that next time. There's a go-to, like go-to name. Right, this just translates to like, you know, at name, you know, 0 jump. Just jump. And then there's if go-to name. Right? What this means is pop a value from the stack, pop the top value from the stack, and if it is true, then jump to that name, otherwise don't. Okay, so pop from stack, and then jump if true. We're just going to assume that the top value on the stack is going to be either a true or a false, that is like all ones or all zeros, and then we just jump based on that. So in the virtual machine language, if you wanted to have like an if statement that said, you know, if x is less than y, blah, 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 how would you do that? Well, you first say push x, then push y, and then do like an LT instruction that will compare them and then push the Boolean result in the stack. And then you say if go to, right? Which will take that Boolean value from the stack and then jump based on that thing. We'll probably talk more at some point about like, okay, how do we actually write virtual machine programs? Right now we're just translating them, so we don't necessarily need to understand how you write them, but it is helpful to kind of understand what's going on. That's it. That's the only branching things that the virtual machine language gives us. So notice in particular, the virtual machine doesn't really give us like if statements that you would think of where you have like an if and an else. You kind of have to encode that using a bunch of if go-tos and putting your own labels. It doesn't give us while loops. You have to encode that by putting labels and like jumping, you know. Again, that's like the compiler from the high-level language is going to take, that high-level language does have things like while loops and if statements, and it's going to have to translate them down into if go-tos and labels. Yeah.
So to do like an if else, would you have like an if go to name and then just a go to name, or like
Yeah.
two ifs?
Yeah, no, you probably don't have two ifs, because the else just means like, yeah, you have like an if go to, and if it's true, then it's going to jump to here. If it's false, it's just going to keep going. So this would be like the else part up here, and then at the end of the else, you just jump past the then part. Yeah. Yep. We'll talk more about that. We'll talk a lot more about that, you know, like next week or sometime. Okay, so that's it. So any questions about that? Obviously, like, this is real assembly, this is real assembly, this is pseudo assembly, like, this is multiple instructions of assembly, but at this point, hopefully you can figure out how to do that. We've talked about popping from the stack and stuff. All right, function calls. So I'm just going to kind of introduce some, you know, major concepts here right now, and then we'll spend all Thursday talking in detail about how function calls work, because it's not simple. It's not necessarily hard, but it's not simple. And this is like a main feature that the virtual machine gives us that kind of distinguishes it from, because so far it's like, okay, this kind of feels like, you know, a different kind of assembly language. It's like we have jumps, we have, you know, we have some different kind of instructions, and we have this stack thing. Okay, that's different, but the function calls is like the main thing that's. All right, so. So there's 3 VM instructions that have to do with function calls. There's one that says function name, and I guess I'm like underlining things to say like, that's not literally part of the syntax, that's just like, that would be replaced by something. So, you know, like the word function is actually this, you know, the syntax of that instruction. It's the function instruction. But then here you would put some name and you put some number in. So you could say like, you know, function F3 or function G9 or something. So this is like the name of the function. And this is the number of local variables. And this basically just declares, hey, this is the beginning, like, everything that comes after this is going to be the code for this function. So if you want to call this function, you should jump here and do these instructions. Right, so this is like defining a new function. Why do you, anyone have a guess? Why do you think we need to know the number of local variables for the function?
Local?
What was that?
For local?
For local, what do you mean? I think you're on the right track.
It was at the top. The things, one of the registers.
Right. Yeah. So it has to do with there's that local register that points to the local segment. That's like where that function's local variable is stored. Why would we need to know specifically how many there are?
To figure out where pointer starts.
I mean, yeah, that's the right idea. I mean, we need to know because we need to know how much memory
Oh.
we need to store them, right? And that will affect, like, yeah, where the pointer is, or where it affects, because we literally, like, we have to put things exactly where we want them in memory, so we have to know where we're going to store those and how much space they're going to take. There is an instruction called call name m. So this is calling a function, of course, right? So this is call a function. That's, of course, the name of the function you're going to call. This m is the number of arguments. Because as I hinted at before, in one example I did, the way you call a function, if it takes some arguments, you first push the function's arguments on the stack, and then you call the function. And the function expects to see its arguments sitting there on the top of the stack for it. But you have to say, like, how many did you push? Because, like, that's the way, there's no way to tell. Like, the stack is just like a bunch of stuff. Which part of the stack is the function arguments? Right, so you have to say, you're like, okay, there's two things I just pushed on the stack. That's the function's arguments. And the last thing is return. Okay, which of course means exactly what you think. Return a function. Right, so when I say call, it's going to go start running the code for that function, and then when that executes a return, it's going to jump back to where it was before. Now, of course, how does it know where to jump back? Well, we have to tell it. I mean, at the level of the virtual machine, if you're writing virtual machine code, you don't worry about it. You just say, yeah, call this function, return. It does exactly what you would think, right? But of course, at some level, something has to be keeping track of all that stuff. And like, where do we jump back to when we're done? How do we know, where we find that? So that's what that's what the translator has to do. It has to generate some assembly that's going to keep track of that stuff for us. Cool. Any questions about this? Simon?
Will this support recursive function calls?
Does it support recursive function calls? Yes, absolutely. And part of, so we'll talk more about this next time. Part of the way that works is that every time you call a function, it kind of saves the function's current state and then pushes some new stuff on the stack that for the new function call. And so it doesn't really matter if you're calling another function or yourself, it's still going to do that same thing. So if I'm in the middle of running a function, the function calls itself, it saves the state and then goes and pushes some more stuff on the stack for that next call. And then when that call's finished, we come back and we keep running the previous call of that function. So there's really, at the level of, like, we don't really have to do anything special in particular to support recursive function calls. It just works. And I think for sure we will write some code in the high-level language that is recursive, and it should work. Any other questions? All right. Next time we'll talk about how we're actually going to make these work. So, see y'all on Thursday.
I gotta do proof and stats. I gotta get Huh?
A little bit more.
Was it a meeting?
Because we did, one more activity for this week, last
Oh,
week.
bad.
So, yeah.
Okay, good, food time.